All right, this video has a few more examples of integration by parts. And after this, you should have everything you need to know to do some of the MyLabs Plus online problems. The main example I wanted to show here is one where we have to use integration by parts twice. Like I said before, the essence of integration by parts and substitution is that it really is a way of rewriting an integral as another integral. And so it's often, our integration rules are really just one step of a process. And in some problems, there may be 2 or 3 steps to actually get to the final answer. In this case, the first problem here, we have an algebraic function x squared times a trig function. And so we know that, that a solid choice for our u and v prime in integration by parts is for the u to be the algebraic part. And if u is x squared, then u prime is 2x. And 2x. And if v prime is sine of x over 2, again, this is an antiderivative problem, so we have to be careful here. But the antiderivative of sine is negative cosine. And actually, let me give myself some space here. So I'll have negative cosine, but the 1/2 factor that's inside the parentheses, that's x over 2, so that's really 1/2 x. The rules that our elementary rules that were on the first page of the previous worksheet point out to us that when we do the antiderivative rules with a constant times x, we get the reciprocal of that constant out in front. So putting all that together means that the antiderivative of sine of x over 2 is negative 2 cosine x over 2. And you should always take a second here and make sure this makes sense. Think about what the derivative of this would be. With the chain rule, the derivative of this would be negative 2 times negative sine x over 2 times 1/2. So that times 1/2 that happens by the chain rule is going to hit that 2, and that's what's going to leave us with just the sine of x over 2. Okay, so integration by parts says that I should get u times v. So I'll write that negative 2x squared cosine x over 2. Usually like that negative sign to be, the negative sign of the constants to be out front. And then minus the integral of u prime v. So this second row here. Now the second row I'll have a 2x and a negative 2. That'll be negative 4x. And so a negative 4 constant is going to be plus 4 outside. So I took the subtraction from integration by parts and realized that I was going to have minus negative 4 times something, and I made that positive 4. And so integration by parts works perfectly. It just gives us a new integral here that we also don't know. But if you look at it, this is an algebraic part times a trig function. This is perfectly set up for integration by parts a second time. So for the second time, I'll have u equals x, v prime equals cosine x over 2. So the product of those two things is the thing I'm trying to integrate. So this is my integral. If u is x, then u prime is 1. And if v prime is cosine x over 2, then v will be 2 sine of x over 2. That 2 out in front for the same reason we were just talking about for the previous one. Now, keeping the plus and minus sign straight is a little bit of a challenge here, so let me just advocate for gratuitous parentheses if you're not sure. So everything I'm going to say about the answer to this new integral is going to go in the parentheses. And by putting it all in parentheses, and I'm sort of kicking down the road the part where I have to pay attention to that. It's really hard to keep all this straight if you try to do it in your head as you go. Okay, so so this integral is u times v, so that's x times 2 sine x over 2, so 2x sine x over 2, minus the integral. I'm going to erase some of this now. So it'll be the integral of this bottom line. So the integral of 1 times 2 sine of x over 2. So I can remember that. So I'll have here, oops. So I'll have here inside here 2 times sine of x over 2, all in parentheses. So the integral of 2 sine x over 2, that's actually just one of my basic formulas. Sine of ax, remember we said was negative cosine, or negative 1 over a cosine ax. It's actually the same antiderivative that I did here. When I went from this line to this line up here, I've said the antiderivative of sine of x over 2 was negative 2 cosine x over 2. So the same thing's going to happen here. I just have an extra factor of 2 out there. So now I'm ready to write the whole thing down. So this is negative 2x squared cosine cosine x over 2 plus 4 times that quantity. So I'm going to distribute that 4 through. 4 times 2x will be 8x sine of x over 2. And then this 4 will be times this minus this, but this integral here is going to be minus something. So this will be minus minus. So you might take an extra step there just to make sure. But what's going to happen is this minus is going to become a plus. There's going to be an extra factor of 2 to hit this 2, which is also multiplied by this 4. So all of that together means I'll have plus 16 cosine x over 2. And of course, plus c. It's an indefinite integral. One thing I do want to point out is that if we wanted to check our answer here, and it's not a bad idea with something like this because of all the crazy plus and minus signs, we can always check an antiderivative question with derivatives, but the check will use the product rule for sure. Since the integral used integration by parts, the checking with derivatives will use the product rule. And in this case, it's going to use the product rule twice, because you'll have a product rule here, and then you'll have a product rule here, and then you'll just have a regular chain rule there. But if you do all that, I do recommend it because not just for checking answers, but it'll actually give you more insight into what integration parts is doing. So what's going to happen here is when you do the product rule here, one of the two terms is going to be this thing we're trying to integrate. The other term that pops up is going to be canceled out by one of the terms in this product rule. And the term that doesn't cancel out in this product rule will pop up and then will be canceled out by the derivative of this guy. And so what happens is you have this sort of chain reaction of things canceling out until you've canceled everything, except for the very first thing, which was your integram. So it does give you some insight into why it works. And so I do recommend at least once or twice checking one of your answers using the product rule. Okay. This next question, our rule of thumb for choosing u says that we should use u equals the log function, which means that v prime will have to be the square root function, which I know I'm going to write x to the 1/2 because I know I'm going to have to use some power rule with it. In that case, u prime is 1 over x, and v, remember this is an antiderivative. The power is going to go up by 1, so from 1/2 to 3/2, and then I'm going to inherit the reciprocal of that new power outside. So that's the antiderivative of x to the 1/2. So using that, using integration by parts, now I'll have u times v. So that's 2/3 x to the 3/2 log of x. This is a definite integral, so I know I can evaluate it as I go. So I can go ahead and evaluate that from 1 to 4. Then I'll have minus the new integral over the same interval will be the integral of the product of these two things. So let's just think a second about what that will look like. This x in the denominator is going to cancel with one of these x's. This is x to the 1/2, so canceling with one x will leave you with an x to the 1/2 here. And then, of course, I'll have the 2/3 there. So so what I'll end up with in the integrand is a 2/3, which I usually write out in front, and then x to the 1/2. So that x to the 1/2 that's there is not because of the original x to the 1/2. It's because this was x to the 3/2, and then it got multiplied by 1 over x. So those two things multiplied together gave me x to the 1/2. All right, so then I can just plug in the numbers. So putting in 4 if you put 1 into this, you'll have 2/3 of 1 times log of 1, which is 0. So in this case, it'll be subtracting 0. Then I'll have 2/3. The antiderivative of x to the 1/2, we just did that. That's 2/3 x to the 3/2, and that's evaluated from 1 to 4. And so I'd be plugging those numbers in as well. So whatever that turns out to be. There are answers on the second page of this if you want to try it and then check your answers. The interesting thing about that problem is that there was really nothing special about that x to the 1/2. If you try that, walking through that with this instead, u equals log x, v prime equals x to any power at all, other than the -1 power, you can actually do the integration by parts steps, leaving n as a parameter, and you'll get an answer that actually has n's in it. So that's not a bad exercise. It'll get you some practice at using something with a parameter in it, and the answers are on page 2. So it's not an assigned problem, but it's something that it might build some insight for you to do it. What I do want to show you is what we call reduction formulas, because these do tend to come up. A lot of engineering and physics books still have tables of integrals for particular kinds of problems. And so I did want you to at least see where they come from and get some experience with plugging numbers into them. So here we have an n and an a in this problem that are, we want to think of them as just numbers that we don't know. So they're not the variable in the integration, they're just numbers we don't know. So it would be like in the formula for the one I just talked about up here, if you read this formula and read that with n equals 1/2, then that would be that problem, the part 2 problem there. So we think of the n in these things as being a number, but we just don't know what number it is, but we can do the whole problem without actually knowing that. So same thing's going to happen here. The choice of u and v prime is going to be this. U equals x to the n, v prime is e to the ax. Again, that's using our LIATE hierarchy. The x to the n part is algebraic. Anything that's like x squared, x cubed, square root of x, those are all considered algebraic functions. And of course, e to the whatever is an exponential function. So we never ever would let, well, in any of the problems that we'll do, we'll never let u equals an exponential function. So u prime would be the derivative of u, and so I can write that down. I don't need to know what n is to know what the formula is for that, so I can just write it down as the formula, if I could write carefully enough. And then the same thing, e to the ax is antiderivative. That's one of those things on that sheet. So we know that's just that. Antiderivative e to the x is e to the x, and I know that I'm going to get the reciprocal of that constant a when I do the problem in general. So if I use integration by parts, I'll have that the integral of x to the n e to the ax is equal to u times v, so 1 over a x to the n e to the ax minus, we won't write that quite yet, I'll miss a little space, minus the integral of u prime v, so these two guys. So in this formula, the n is a number, an unspecified number. The 1 over a is an unspecified number. So when I'll go ahead and multiply those two things together, n times 1 over a, and like I've been doing in other problems, I'll pull that out in front of the integral. Since that does not have an x in it, the x is the variable for integration, there's nothing wrong with doing that. And then inside the integral, I'll have x to the n minus 1 e to the ax. So that gives me what I call a reduction formula. The reason it's called a reduction formula is that it tells me the answer to an integral with a power n in terms of an integral that's exactly the same form, but with the power that's 1 less. And so it allows me to take an integral of say, something that has x to the cube e to the ax and reduce that to an integral with x to the squared e to the ax. The benefit of that is to be able to quickly do problems like the very first one we did up here, where it might have integration by parts twice, and I don't want to go through all of this extra work to make sure with all these places where I could mess up the derivatives and antiderivatives and stuff. Working with these things is a lot easier. So for example, let me just give myself some space here. So for example, if I want to do the antiderivative of x squared e to the negative 2x, and I want to use this reduction formula, I would think, okay, well, in my reduction formula, if n is 2 and a is negative 2, then the problem I have up there matches the left-hand side of my formula. So now I can just write down what the right-hand side of my formula would be when n equals 2 and a equals negative 2. So I have 1 over a, so 1 over negative 2, x squared, e to the minus 2x, minus, and then in the formula I have n over a. Well, n over a is 2 over negative 2, so that's negative 1. So this negative will become a positive, and I'll have x to the first power, e to the minus 2x. So without having to explicitly do the integration by parts, I can just use the formula for that. So now I look at it, and I see that this is now an example of this formula where n equals 1 and a is still negative 2. So I can keep my minus 1/2 x squared e to the minus 2x that I had before, and then I can just give myself some parentheses and then use the formula again. So I'm going to copy down this side of the formula using n equals 1 and a equals negative 2. So negative 1/2 x to the 1 e to the minus 2x is what I'll have from this term. And then I have minus n over a is going to be 1 over negative 2. So that's negative 1/2. So I'll make this plus 1/2 times the integral of x to the 0 e to the minus 2x. At this point, x to the 0 is 1. So at this point, this is just a normal integral of e to the minus 2x. So I know what that is. And so now I can just write down all the pieces that I have. And then this final integral antiderivative of e to the minus 2x is negative 1/2 e to the minus 2x. And so multiplying that by 1/2. So this will be my final answer. It really is the same as just using integration by parts twice that I did up in the first part. But the path through it feels different when you're plugging into a formula rather than explicitly doing this integration by parts work at each level. It's really equivalent to doing the integration by parts every time, but you can do it a lot quicker if you just use the reduction formula.